Thank you for joining us bright and early for today's first Fast Pitch session. Today's session is on next generation. We will have 5 8-minute presentations on what we see as the next big opportunities in energy generation. There will be time for Q&A at the end of the session, so I encourage you to submit your questions in the Summit app. And without further ado, let's get started. I'm happy to hand it over to Rob Mellors, who will be doing our first presentation on subsea geothermal.
Good morning again. So I'm going to talk about a vast untapped resource below the oceans, seafloor geothermal, and it's completely untapped and terawatts or gigawatts of potential. And so, yeah, I'm Rob Mellors, and I'll be talking about the potential, the benefits, and the path forward. First, this is a map of the world. And so the red zones are areas where magma is welling up from the mantle, creating hot rock at the surface. So it's a vast volcanic chain of mountains. And you'll see there's a few places, Western US, Iceland, East Africa, where these volcanoes come on shore. And these areas are hotbeds of geothermal activity. For example, Iceland gets 65% of its energy from geothermal. But you'll see most of this red zones are under the oceans. They're completely untapped. So there's thousands of miles of volcanic mountains of very hot rock with energy that is completely available. So, let's step back. And what is geothermal energy anyway? So typically onshore, you drill a borehole into the ground, hot water and steam come up, it drives a turbine, that drives a generator, and it produces megawatts of electricity. You might get 10 megawatts per well, and then often it's re-injected in the ground. Worldwide, geothermal provides about 16 gigawatts of energy, and about 4 gigawatts in the US, and there's a lot used for thermal as well. And right now, 100% of geothermal power is from onshore sources. And on the left, you'll see, you'll see a picture of a plant in Iceland producing power. So seafloor geothermal, here's a cartoon of where you see the magma welling up under a spreading center. And here the hot rock, it's maybe 800 or 1,000 degrees centigrade, comes up very close to seafloor and will actually erupt in places. And so this is a vast resource. It's very shallow. It's less than 1 or 2 kilometers below the seafloor. In fact, in some places, it's so shallow, the water goes down and it fractures in the rock, and then it flows up, and you get these hot plumes coming out of the seafloor. And so the potential here, it's probably tens of gigawatts, maybe 100, maybe even more. It's also the only available power source or renewable power source in the deep ocean. So what can we use this for? One possibility is we could use it for power for islands and coasts, for example, Hawaii. Rather than using valuable real estate on the island itself, you could put a geothermal facility in the ocean and just pipe the power onshore through a high voltage DC direct current line, for example. Or you could do the same on the west coast of the US, supplement the onshore grid, or maybe there's a data center that needs power. Another possible use is for exploration and operations in the deep ocean. Suppose we have seafloor mining looking for critical minerals on the seafloor, manganese nodules. This would be autonomous robots going down. Typically they're powered by batteries or by a tether to the surface. But if you have a kilometer-long tether, that's very bulky. Batteries require charging. Now you have to go up to the surface and back down. What if you had a plug-in station essentially right there on the seafloor, powered by geothermal? The autonomous robots would go over, they'd plug in, they would power it, and they would save enormous amounts of time and effort. And you could use it for other things. You could generate hydrogen, or you could use it for aquaculture. Of course, it is deep and there's problems. It's very high pressure. You're at 1 to 3 kilometers, so you've got pressure hundreds of times that at the surface. It's also cold, maybe 3 degrees, dark, and if you stir up the silt, you may lose visibility for minutes to hours. But right now is a time of really rapid progress in automated robotics and autonomous vehicles. They're being designed to do all sorts of operations in the deep sea, and so now the time is right. We can do that. We can install facilities down there without any direct human intervention except on the surface. So how do we access this energy? Well, we could drill boreholes just as you do on land. Drilling off ships is a very mature technology. It's somewhat expensive, but it's certainly possible. It may get interrupted by weather. An alternative is these places where the hot fluid is coming up out of the seafloor. We could access this hot fluid directly. And here's a picture of one. For example, it's about 300 degrees centigrade. Because of the extreme pressure, it doesn't convert flash to steam. It remains a liquid. Some places it's supercritical. And it's dark because it's loaded with minerals, some of which can be valuable. So we could access those flumes without drilling at all. So one way to to turn this into power would be just turbines, just like we do on land. And so here, because you want a lot of flow, you would probably have a borehole, you'd have fluid coming out, and then it would go to a turbine and drive a generator. You'd have to put all that into a pressure shell so it's protected from the high pressures around it. Now, one big advantage of the ocean is that on land, we need cooling towers to cool the outlet fluid. In the sea, all the water is 3 degrees centigrade, so you don't need a cooling tower. You've got an ample supply of cooling liquid all around it to make maximum efficiency. So that's one possibility. Of course, you'd have to make it very robust, so there's low maintenance, or maybe you would make it modular so that you could just completely swap out the generator in one go. There is an alternative, though, and this would be using thermoelectric units. And so thermoelectric units depend on pressure, on the temperature differential to create electricity. One side is hot, the other side is cold. That creates current between them. And so you can use that. And because in the ocean we have the hot fluid coming out of there, you have a heat exchanger sticking into that hot fluid. That goes to one side of the thermoelectric unit. You've got cold water from the ocean on the other side. That could generate probably tens of watts. It'd be difficult to get megawatt range, but you could certainly get kilowatts range. And so that's the kind of thing you could use for a recharging unit. You might have batteries or supercapacitors there to charge up and have it reliable. One problem is that these fluids coming out, as you can see, they're very dark and loaded with minerals. As they cool, you'll get precipitate and scaling on the heat exchanger. And so you need materials that are resistant to scaling, or maybe some sort of liner that you could put and remove, because these are actually valuable materials. So that's one challenge we have to address, and we have to work on scaling the thermoelectric. But thermoelectrics are used in spacecraft that go for decades, and so the big advantage is that there's no moving parts and low maintenance, although the efficiency is not as great. So next steps, we need sensors to detect these underground, hydrothermal vents and areas of high heat flow. You need the ability to drill in the ocean. We need the ability to create submersible turbines and materials resistant to scaling and corrosion, specialists, geothermal specialists, and many other capabilities. But it's a vast resource, and I suggest we go forward and access it. Thank you. And now I'll hand it off to Johan. Thank you.
Thanks, Rob. Great. I think we are in sort of sync here a little bit. We just get to the right slide, right? So I'm going to talk about pump batteries. Pump batteries, right? So these are not regular batteries, as you would see, but it's tried to rejuvenate long-term energy storage using existing infrastructure on land. Right, so if we think about, what's happening today in our electrical infrastructure, there's a lot of new sources coming to our grid, talking about Rob's sort of ideas. We're looking at a lot of new loads. And of course, our grid per se and our electrical infrastructure is not as resilient as we would like to have it. Right, so there's currently 1.3 terawatt of generation sitting in the queue. we have about 3 to 4 terawatt of new loads to be connected. And by the way, it costs us about $150 billion per year to actually make this work every year, to actually get it to be more resilient. So we need very high dynamic grid storage to really balance the energies, these highly dynamic loads, these new generation sources, and be resilient. So if you think about that, we need a lot more energy storage, especially long-term energy storage. Right, so let's look at the best working principle of long-term storage. That is actually pumped storage hydro. Pumped storage hydro has been around since the 1930s. We actually use it for nuclear generation, all our base load, since the 1960s. And it is a great technology. It does the work. It's very clean generation. It is what it is. We all know it. What's the problem then? It's limited in terms of where we can build new ones. We have to build new dams. The round-trip efficiency is not that greatest. And the dynamic performance, if we think about these dynamic loads, data centers, and all the loads we put to the grid, they just don't have a dynamic performance we would like. The grid support functions are also not there. It basically, one day it pumps up, and the next day it pumps down. So what can we do with that to make it better, right? So I think the next steps is to look at much more sites, not new dams, but locations where we can use pump hydro. Improve the dynamic performance of existing pump storage hydro, but also for all these new ones we want to build out. And thirdly, I really think a lot of our technology needs to be subsurface. It has to be underground in order to make this work. Right, so okay, let's look a little bit at pump storage hydro. Existing plants, there are about 42 plants in the country today. They generate 22 gigawatts of power, which is about a quarter of our nuclear fleet. And on top of that, they are actually pumping up and down on a daily basis. They're highly distributed, actually across the nation, and they are generating per site about 1 gigawatt hour per site. It's typically a cycle of 8 hours up, 8 hours down. So it's a really great technology. It is just too little and it's not dynamic. Let's look at gas wells. There are about 6.7 million gas wells out there. A lot of those are abandoned. So of those resources, which are also highly distributed across the nation, are all those resources ready for us to use pump hydro? Yes. There's several studies who shows that there's probably 10 to 100 terawatt hours potential of hydro, pump hydro in these wells. It's a very simple equation. If you take power and you have flow rate and you have height, or head as we call it, you really get a lot of power. So either increase the flow rate or have a larger height and you can get much more power. So it makes all sense. But let's look at mines, retired mines. Can we actually look at retired mines as an asset where we do really anticipate these are also highly distributed across our country, and we can actually utilize underground reservoirs, underground tunnels, underground shafts, and to put our technology right in the middle of us and actually use that as gravitational energy to do pump storage without building new dams, without building any subsurface infrastructure. Right, we actually do have a company here, right here at our booth, Quitnet, which actually start doing this by actually pressurizing the water going down shaft in existing mines or areas where this is available, and actually use this as a pump storage solution. Their solution is actually up on the surface. The pump technology is up on the surface. So there are some opportunities to get a lot of that downhole. Right, so go and visit them. They built these modules of 1 to 10 megawatts, which you can actually get up to 10 hours of storage. Right, so what disruptive technology do we need to make these things work? Right, conventionally we have a pump, we have a generator, we have a lot of times mechanical valves to control the water flow? Can we start integrating that much more? Taking the turbine, taking the generator, taking the power electronics now because we need dynamics, and build that all very highly integrated using high-speed generators, high voltage cable technology, which can go very deep areas, which can operate in high pressures, and can actually have operation in high hazardous environments like coal ash and methane gas. And if we can make that work and get the cables down to the point right at the converter level, compact these pumps, drives, and power electronics, and we can put them down shaft, we actually have pump storage right there at our doorstep. So anyway, if you are interested in looking at long-term energy storage on existing infrastructure, come and talk to me with ARPA at the ARPA-E coffee coming up, and that will be tomorrow, 7:30 to 8:30. Thank you. And we've got Jim here, who's going to talk about carbon.
Thanks, Johan. Excellent talk. Good morning, everybody. My name's Jim Seaba, Program Director here at ARPA-E. Real pleasure to be with you this morning, and thanks so much for coming. This morning, I'd like to talk to you about carbon as the next generation fuel. So I said carbon, not hydrocarbon. I came out of the oil and gas industry, so I know the difference. I really want to focus on just carbon. And then why do I want to look at carbon? And if we can use carbon as a fuel, is it going to be affordable and sustainable? So first of all, the very interesting thing about carbon, it has a fairly high energy density. Right now, liquid fuels, hydrocarbon fuels, as you know, jet and diesel fuel, are at the top of the energy density list. That's why we use them in our jets and our planes, et cetera, right? Highest energy density. Carbon has twice the energy density of carbon and diesel fuel, twice the energy density on a volumetric basis. That is substantial. However, the problem with carbon, it's actually very difficult to oxidize high purity carbon. However, electrochemistry can unlock this energy potential. So that's really what I want to talk to you today about, is unlocking that potential for carbon. So yes, I said electrochemistry, which brings up two four-letter words, fuel cells. So I understand some people could be automatically concerned by that from a commercialization standpoint, but I wanted to help alleviate those concerns and kind of enlighten everybody where we're at today in this space. So if we look at the graph here, the volumetric energy density on the y-axis, gravimetric energy density on the x-axis, and let's go from the lower left and head up toward the right. Lower left being our lithium-ion batteries, and the green dot there is our direct carbon fuel cell. All right, and so our lithium-ion battery, as we know, we get like 300 miles now plus per charge for these electric vehicles. They made great progress. They're commercialized. I mean, who would have guessed lithium-ion batteries would be, coming on the scene, and we have all these electric cars today. That's kind of incredible. ARPA-E has seen that and already has a program to double the energy performance for these batteries, and that's Propel 1K. And you can see that down in the tech showcase, and I definitely recommend you to see all the performers there looking at next generation batteries. And again, that was going to double lithium ion. If you look at where direct carbon fuel cells, where we place this on the map, it's 8 times the energy performance of lithium ion batteries, 8 times. Meaning again, if I had a lithium ion battery and I instead took that out and put in, let's say, a direct carbon fuel cell, kind of like a battery, and put it in there, instead of going the 300 miles, I'd go 2,500 miles. And I could use heavy duty, so I can go cross country on a single charge. It's very interesting. All right, where do I get this dot? Why do we place it there? Well, we leveraged our technology and information from our REACH program, where we've been developing solid oxide fuel cells for the last 5 years. We've made significant progress. Again, they're down in the tech showcase, and we can go see those later. But the important part is we've greatly reduced the manufacturing costs of solid oxide fuel cells and tripled the performance and energy density of that. And so there's definitely these metal-supported solid oxide fuel cells, I think, are really an enabler for then this direct carbon fuel cells, and you can use the same chemistry. So again, going back to number one, direct carbon combustion is challenging, or basically you cannot take high purity carbon, put it in any commercial combustion process today, it will not burn. All right, put it into a boiler, nothing will happen, you'll extinguish your flame. All right, so therefore, again, as I talked about, we're going to look at direct carbon fuel cells. The other thing about carbon, it has the highest efficiency of any fuel for a fuel cell, theoretically. And we're going to have a target efficiency of 80%. So now, again, we're dealing with a material that has twice the energy density of the jet fuel, and I'm going to convert that energy, 80% of it, to electrons. So there gives you this high energy performance potential that I'm very, very interested in. This just shows you an example of a direct carbon fuel cell. I told you there's other chemistries, but for simplicity, let's just look at the solid oxide fuel cell. And on the right-hand side, the cathode electrolyte here is identical to that of a solid oxide fuel cell. And for simplicity, I'll just put in carbon as the anode. And in this case, I'm just going to eat the anode away. Oxidize the anode, CO2 comes off. Of course, when the anode runs out, the fuel cell's dead. Or in other words, basically, it's an air-breathing battery. So we can leverage the battery programs like Propel 1K. We can leverage our REACH program where we develop solid oxide fuel cells. And honestly, if you listen to Ryan's talk yesterday about plasmas, we can even leverage plasma technologies because, again, what we're talking about is using these oxygen ions to basically do our oxidation process for us. That's what we need. Because again, combustion can't do it, and why can fuel cells do it? It's all around basically looking at electrons and ions to do the work for us now. All right, first of all, proof of concept has already been done for you. That's great, so this can be done, it's not impossible. All right, as I told you, solid oxide has been used in the past, and also molten carbonate, molten hydroxide, aqueous hydroxides. These are higher temperature fuel cells, 400 to 800 degrees C. Unfortunately, only single cell experiments were done, and they use carbon materials basically from a derivative of coal, and the other non-carbon species in there really kill the electrochemistry process. So where do we get the really pure carbon, and how are we going to make that affordable and it's scalable for fuel type of arrangements? Well, let's look at biomass. Recently, we looked at biomass for sequestering carbon, and we come up with processes that can take biomass and convert that into high purity carbon. We have that today. And plants, by chance, or by Mother Nature, is over 50% carbon. And recently, we've come up with plants that can grow a lot of carbon. On the right-hand side, you'll see that where that gentleman is standing in front of Macathis, which is basically a plant that can grow up to 10 tons of carbon per acre. Now, what does that mean? Well, that means that if we take the carbon from those plants and then put it into a direct carbon fuel cell and again, achieves our transportation needs, and compare that, let's say, with $3 per gallon for fuel to do the same amount of work, that means it's $800 per ton for that carbon at $3 a gallon, which means it's $8,000 an acre. All right, I came from the Midwest. $8,000 an acre is a pipe dream. All right, but they grow corn. They're doing good to get $1,000 to $1,400 an acre. And in addition to that, they have to use a lot of fertilizers, etc. And with these plants, a lot less fertilizer. Of course, it's a perennial plant. Almost no pesticides are required, and a lot less water. So from a really farming and even ranching perspective, wow, we have a great opportunity here. And also on the left-hand side, you'll see that we have plenty of farmland, and for us to even meet the goals of fuel and diesel needs, it's only 4% of our total agriculture crop. So again, it's not that bad. So I'd like to unlock this carbon to deliver, the next generation fuel, and I'd like you to come and talk to me about that. We really need to focus on this direct carbon fuel technology to enable this to happen. Thank you very much. Who's next? Oh, sorry, and Elise will be our next speaker here. Elise, thank you. Yeah.
Thank you, Jim, for the introduction. Did you know that 1 gram of uranium can produce as much energy as 3 tons of coal? And And it could produce even more, because right now we only use about 1/3 of its energy. Today I'm going to talk to you about direct energy conversion and how it could revolutionize the way that we use nuclear energy. Direct energy conversion is simply the conversion of energy into electricity without the use of heat as an intermediary. We've essentially been making electricity the same way since the first steam turbine generator was built in 1884. A fuel is used to produce heat, which is used to make steam, to turn a turbine, to turn a generator, to produce electricity. So it makes sense that when the first nuclear power plant was built in 1951, it used steam-based thermal generation. But as we design new nuclear power plants, and we even imagine using fusion for energy for the first time, is this really the best way to make use of the energy in nuclear reactions? With the upcoming nuclear renaissance, now is the perfect time to reconsider energy conversion from nuclear systems. All thermal power plants, be it coal, geothermal, nuclear fission, even nuclear fusion, work by the same basic principle. And these power plants make up over 80% of all electricity production. And if you think about it, they're all really just fancy ways of boiling water. Are we really going to go to all the trouble of making fusion happen just to use it to boil water? Now, thermal generation makes sense for fuel sources like fossil fuels, where the primary output is heat. But nuclear is different. In a nuclear power plant, the fuel is uranium. The splitting of the uranium atom produces fission products, neutrons, and gamma radiation, which interact with surrounding atoms to produce alpha and beta radiation. The way that we harness these products right now is by letting them collide with the surrounding materials to transfer their kinetic energy as heat. But at each of the subsequent conversion steps, energy is lost, so that by the time electricity is produced, over 2/3 of the energy in the fuel has been lost. The plants are only about 30% efficient. And the vast majority of the losses occur in the conversion of heat into electricity. The concentrated energy of the fission process is essentially downgraded to heat and then converted back to electricity. But if we think of the primary product of the nuclear reactions not as heat, but as the particles and radiation that they produce, then there's an opportunity for direct conversion. Instead of letting it be converted to heat, and then in turn converting that to electricity, can we use the energy in the radiation directly? When ionizing radiation interacts with matter, it produces both heat and ionization, with about 40 to 50% of the energy going into ionization. Right now, we don't use that energy directly, and only the heat gets converted into electricity. Direct energy systems could use the ions generated in materials to produce usable electricity. And by combining direct and thermal conversion, overall system efficiency could be more than doubled. Or, if using direct conversion on its own, efficiency could be increased by cutting out conversion losses. And by limiting the need for turbo machinery, it could also reduce the size and cost of the balance of plant, which can be over 50% of the total cost of a nuclear power plant. This reduction in complexity would also mean fewer moving parts, less maintenance, and higher reliability, potentially opening up the opportunity to use nuclear in remote locations. Now, I want to be very clear here. Direct conversion would be no matter of a simple drop-in replacement for the energy-converting balance of plant. This is because current nuclear cores are designed not to have any radiation coming out of them, understandably. So the entire reactor would need to be rethought and redesigned to make access to the radiation possible for direct conversion. Now, how does direct conversion work? The radiation produced by nuclear reactors has enough energy that it can detach electrons from atoms, producing ions. The ions have an electric charge, so they can then be used to produce electricity. The interaction of radiation with matter can produce ionization in different forms. But regardless of the form, there are two fundamental challenges that have made it hard to implement direct conversion and would need to be overcome to make effective conversion systems. The first challenge is that the size of the conversion device must be matched to the path length of radiation transport in the materials. Different types of radiation travel different distances in materials, ranging from tens of microns to multiple meters. But all of these distances are much larger than the size of a typical energy conversion device. The second challenge stems from the interaction of radiation with the atomic structure of the materials themselves. Radiation interacts strongly with materials, so it changes them as it interacts, creating defects and damage that make it very hard to maintain long-term performance. We can use radiovoltaic cells as an example of how these challenges present in an actual energy converting device. Radiovoltaics work similarly to solar cells, except the electron-hole pairs are created by alpha or beta radiation incident on the cells instead of the photons from sunlight. The depletion region in a typical radiovoltaic cell is about 1 micron, which is much less than the 10 to 100 micron path length that alpha or beta radiation travels in the crystalline semiconductors that make up the cell. This mismatch in length scales means that while theoretically over 40% of the energy in the radiation could go into making electron-hole pairs, only a very small fraction of them are actually created in the depletion region where they can be turned into electricity. This leads to inherently low efficiency in the devices, with most only achieving about 3%. Additionally, the crystalline semiconductors that make up the radiovoltaic cell have highly specialized structures and doping levels. And as they're exposed to the bombardment of radiation, they are damaged, which leads to very low lifetimes, sometimes only on the order of a few days. Now, how do we overcome these challenges? I by no means have all the answers. That's what I need all of you for. But what if we could use materials that are less prone to radiation damage? Liquid semiconductors, for example, have disordered and potentially self-healing structures that have been shown to have much less degradation when exposed to radiation. The use of liquid semiconductors could thus help to mitigate some of the lifetime issues encountered when using crystalline semiconductors. Or we could bypass these issues by using photon-mediated conversion. In this case, the radiation could be used to excite a fluorescent material to release photons, which would then be converted to electricity by a photovoltaic cell. This way, the radiation is not directly incident on the crystalline semiconductors that make up the photovoltaic panel. Or we could use an electrochemical system to better match the radiation transport distance in order to more effectively capture all of the energy in the radiation. The radiation can be used to create ions and radicals in a liquid through the process of radiolysis in charging tanks that could be scaled to any size to match the radiation source. The activated material could then be discharged through a flow cell to produce electricity. Direct energy conversion has tremendous potential to increase the efficiency and reduce the cost and complexity of nuclear power production. Solar cells started out with an efficiency around a few percent and are now approaching their theoretical maximum efficiency. So I ask you, can we do the same thing for direct conversion for nuclear systems? If you have ideas for direct conversion, how to increase conversion efficiency, or how to integrate direct conversion with nuclear systems, come talk to me at Coffee with ARPA-E tomorrow morning. And with that,
Well done.
Way to go.
I'm happy to hand it over to Bill, who will be our last speaker for today's session. We'll be presenting on nuclear microreactors.
Thank you. I'm Bill Horak, and I'll be talking to you today about small reactors and big opportunities. Now, I want to start off by saying, the Secretary yesterday talked about the need to deploy next generation nuclear technology rapidly. Now, nuclear reactors come in 3 sizes. Venti, grande, and tall. But that's Starbucks, which I did not have enough of today, but the one we're most familiar with right now are large-scale reactors. They're 300 to 1,000 megawatts. We deployed 2 recently, Vogtle, on that. The second one we want to talk about is small modular reactors, 20 megawatts to 300 megawatts, and we're going to have a couple sessions on that later today. But the one I want to talk about today are microreactors. There is no official definition of microreactor. So we being ARPA-E, we made one up. It's 1 megawatt to 20 megawatts. And and the reason I want to talk about that is because microreactors open up new generation markets. They don't compete with the other 2. So basically, the microreactors, they service remote communities, mining, industry applications. Corey Phillips, one of our PDs, is having a nice workshop on Thursday on this if you want to go. And finally, they can be used to balance out energy demand points. Now, the vision for a microreactor is that you build it in a factory, you ship it on a truck, you send it to the site, It operates for 6 to 7 years, and then you send it back. This enables you to have faster installation, lower risk, flexible power. But and there's been several of these, the market is huge for this. This is just one example that was put together by INL that shows potential sites. As you can see, it's across the country and across various regions. So what are we interested in? Right now, there's multiple designs for microreactors. You heard yesterday several times the eVinci reactor being mentioned. We've made investments in that in ARPA-E, and it's essentially out there ready for marketing right now. But there's 10 other ones at least, and we've also made investments in them. So what I want to talk about today is not the design of the microreactor. What I want to talk about is how are you going to make hundreds of these to meet that demand? And we look at it as the key is serial manufacturing. In other words, can you make microreactors and deploy them like you do airliners? And to do that, we have reached out to the manufacturers and said, hey, what's holding you up? What do you need to do to have this happen? So when we talked with them, they said there are several areas that are available for serial manufacturing. The first one was the manufacturing process itself, and I'm going to go into that in a little bit more detail. The second was operation. If you're going to have hundreds of these, how are you going to operate them? A typical nuclear reactor right now requires 22 people for one shift. That's not going to be practical for a microreactor. The third category was alternative fuels. A lot of these use a process that you heard about yesterday called HALEU. So those of that's high assay, low enriched uranium. We can't make enough of it. What's the alternative to that? And finally, control systems. How much of this can we do with autonomous control, which we look upon as an expansion of our Gemini program? So why we're interested in advanced manufacturing? First off, when we talked to everybody, that was the key to reducing the cost and time to reactor operation. We put targets in there that said right now, with a system cost for construction of $50 million, can we get it down to 10? But the most important thing is, can we get the installation time down to 1 month after it leaves the factory? So these are really tough things for us to do. So we came up with several areas. One of them that we want to talk about a little bit is additive manufacturing the fuels itself. Right now, to make a nuclear fuel rod, that's pretty much a handmade process. You put fuel pellets into a rod, you put the rod into bundles, and you put it together. There's been suggestions to do this with additive manufacturing. This not only speeds up the process of making them, but also has the advantage of that you may be able to use lower enriched uranium. The second thing that came back from the manufacturers is, how do we do real-time monitoring inspections? They say the biggest problem they have is they get a component made, they inspect it, and it's not right. They have to dig out the weld, or they have to throw the part away. So how do you do that when you're manufacturing it? So we've looked at several areas. One is just the simplest one. You'd monitor it while you do a camera. But we're looking at other ways to do this inspection in real time. And then the other one is topology optimization for heat exchangers. Again, instead of welding these things together tube by tube, sheet by sheet, you put these together with additive manufacturing. Now, we've already made investments in this. If you go down to the technology showcase, we have two of our performers, Raytheon and Collins, and Boeing, who are demonstrating their additive manufactured heat exchangers. And it's really an incredible thing. Collins is hoping to install this on aircraft in the near future. So what are the other technologies? There's a lot of them. Preventive maintenance. Again, I mentioned this is an extension of what we're doing with the Gemini program. If you have a remote operations on this, you can't fly the people in to fix it. You've got to be certain that that plant will operate for the operating period of up to a year or more. Second is alternative fuels. We talked a little bit about that yesterday. I think there was a mention yesterday in the fission session about uranium nitrides. And finally, autonomous control. How do we get down from 22 people per shift down to maybe 2 or 3? So we're going to be looking at all those things over the next course of our program. So I want to emphasize, to enable the mass market deployment of microreactors, we are going to have to learn how to do this in serial manufacturing. Now, everybody else has talked about, you have an opportunity to talk to them on coffee. Well, Elise and I are going to give you an opportunity to talk to us twice. So if you want, later we're going to have a sidebar session at 3:45 up in Chesapeake 3. You're all invited to come and talk with us and give us your ideas and give us feedback on this. So at this point, I will now turn it back to Elise. Thank you.
All right, great. Thank you, everyone, for the talks. I will remind you that we are taking audience questions. So I encourage you to submit your questions through the app. The instructions are here on the screen. I will start off with a question for Rob, since he kicked off our session. We have somebody who is concerned about induced seismicity. They ask, my understanding is there have been problems with geothermal triggering earthquakes. What precautions would you need to be taken to minimize similar unintended consequences?
So there is some induced seismicity associated with geothermal, but the ocean is a good place to put a geothermal plant. We already have many earthquakes near these ocean ridges already, and so there's no city or urban areas, so even if you have a large earthquake, it probably won't do much damage. And if you're simply tapping the fluid from a hydrothermal vent, these vents have been sending out fluid for millions of years, it won't make any difference. So I would say the risk is low.
Johan, we have a similar question for you. Are there groundwater pollution potentials with flooding wells and mines?
I didn't get that. Sorry.
Are there groundwater pollution potential when flooding wells and mines?
Right. Yeah, that's a good question. I would say there's already the water which is already in there is going to be reused to just be pumped up and down. So in very few cases, you really need to add additional water. So it's basically utilizing the existing aquifers, existing water sources, and some may be polluted already, but you just pump it up and down.
Great. Jim, another similar question for you. Are there problematic impurities in the possible carbon sources?
I'm sorry.
Are there problematic impurities in the potential carbon sources that you described using?
Well, yeah, absolutely. The problem with electrochemical processes and part of the issues they've had in the past to make it a commercialization is, the purity of the fuel and the electrochemistry process being interrupted by that. And so, obviously, whatever carbon source you have, we're going to have to take a look at that, which is, again, why I went to the biomass, because we have a lot more control over the carbon and we can change the plant structures, et cetera, to help determine the best type of carbon combinations that are required that we may need to facilitate a direct carbon type fuel cell.
Great. All right, and now I will take a question for myself. So for a direct conversion nuclear system, how would it deal with the heat? So that is a great question. Any ionization that is not used would usually lead to recombination, which would then produce heat in the materials. So I am by no means a nuclear engineer. I'm a material scientist, so I don't really know how the integration into a power plant would work. But my thought would be that sort of a combined direct conversion and thermal conversion system would be the best. That way you're not throwing away sort of half of the energy. But if you have ideas, come talk to me. Okay, Bill, we have some more people who are concerned about safety. There have been several questions about safety and security for SMRs. Can you comment on that for microreactors?
Sure. So basically, with regards to security for microreactors, as opposed to SMRs. Now, an SMR design is, in effect, a lot of them maintain the same components that you do in the large light water reactors. So you have essentially the same fuel rods. You have essentially the same conversion systems. So a small modular reactor, to a certain extent, looks like a large reactor split up in terms of what you're doing. So the security concerns there are you're on one site, And you can put the guards around it. And in terms of the staffing, what you're concerned about is can the operator operate 6 of these modules instead of just 1? Now with the microreactors, because we're shipping them essentially on the truck and then putting them in operation, we would essentially not have the security issues because it's not fueled the same way. It's all going to be essentially a steady state type thing. More importantly, several of the designs, I hate saying eVinci all the time, but eVinci, for example, with regards to safety, its ultimate heat sink is the ground. Okay, it doesn't require water if it shuts down to maintain cooling. So those are the things that are a big difference. So the security is contained by the different fuel design, much more solid state, and the safety, because in effect, the microreactor is inherently safe with an ultimate heat sink that is either the atmosphere or the ground as opposed to actively pumping water.
Jim, I'm going to throw another question to you. There are many different types of carbon and different sources. Why did you select biomass, and what form of carbon do you need for your system?
Well, that's to be determined on the best form of carbon required for a direct carbon fuel cell. That would be part of the work that needs to be done. And you're right, there are many carbon sources out there that could be utilized. But again, why I chose biomass is, number one, it's very sustainable. Number two, we would have better control of the carbon from that source by just simply changing the soil or changing how the plant's grown or even changing the kinetic codes in the plant. We have those type of levers to pull to help us determine the best type of carbon. And then, of course, obviously, we have large deposits of carbon in the ground, et cetera. But again, mining and cleaning that up is quite expensive. I mean, we would do that today if it was economic, as opposed to putting expensive back-end treatment on coal power plants, for example. So it's all driven by economics. We want the best economic way to deliver that type of carbon. Yeah.
Great. Johan, I have a question for you. They ask, unlike salt mines, the surrounding geological formation for coal mines has significantly higher permeability. Would that be an issue for pumped hydro storage?
So that's for the coal mines, right? Yeah.
Yeah, so the higher permeability.
So again, like for oil wells, a lot of these coal mines are naturally filling up with water or contaminated water. So in the same case, you will basically utilize the existing underground reservoirs and pump the water up and down and stay underground. It doesn't go up, it doesn't go down. So the ideal way would be to have a reservoir in the middle of your mine and a reservoir at the bottom of your mine, and basically pump across these two barriers.
Great. Rob, I have a question for you on pricing. Do you think the power from subsea geothermal can ever be competitive in price with other sources of electricity?
I think it would, for, say, continental, it would be tough, but for places like islands where the supply of electricity is already constrained and higher, it may be competitive there, and it's in kind of ease, and that would be where you would start. But I agree, it would probably be more expensive than onshore geothermal or reactors or others.
Cool. Johan, we actually have a similar question for you. How does the levelized cost of storage for pumped storage hydro compare with grid-level battery storage?
Right, so, that's actually a good question, right? So would you rather put lithium-ion batteries and build it for long-duration energy storage, or would you look at these other options? So, there is a break-even point. A very short-duration energy storage for grid applications, advanced grid support functions and so on. Obviously, your batteries would make sense. We use batteries in our laptops and so on. So it's not to say that the batteries is not cost-effective in certain applications. But if we're talking about long-term energy storage, and that break-even point comes probably at about 8 hours, depending on the technology. But if you have really needs for an 8-hour or longer long-duration storage, it's really very difficult to build this scale of energy storage with batteries. And on top of that, it becomes now an issue of having enough lithium-ion batteries to actually support grid functions, which really is not the best use of lithium-ion batteries.
Yeah. Great. All right, we have a very interesting question for me. So they asked for direct energy conversion. Have you considered how to do energy storage when electricity prices are low, when renewables are meeting grid demand, i.e. the duck curve? So I think this is an interesting question, especially with my last example of using an electrochemical system. In that case, you actually do sort of have built-in storage. So I think that the systems could be designed to sort of allow this type of storage. So in that case, you are charging your electrolyte in your charging tanks, and then you can choose when you want to discharge it. So that does give you sort of an inherent degree of storage. So it's another sort of interesting feature that could be explored as we design new conversion systems. Bill, we have a question for you. Can you provide perspectives on licensing of nuclear microreactors, and how will that impact the 1-month deployment time?
Yeah, we are definitely engaging with the Nuclear Regulatory Commission on how these reactors would be licensed. We've had we just started discussions on them, but we're going to keep that up on a regular basis. Ideally, there's one model that we are looking at, is that you would license them like you do airliners. So a microreactor would get a type certificate. You would then potentially, every reactor that is built to that specification would be licensable. The site part is a little bit trickier. Right now, the site and the construction and the operating license all go together. So how you would do the site permit quickly is one of the things that we're talking with them about. They've talked about things, for example, now that we have satellite monitoring, can we use that to speed up the site license? And then, of course, the last one is how do you do the operator licensing? This is a very different type of operator licensing that is done for the central plants. The NRC has been very helpful in giving us information and interacting with us, and we are setting up a set of regular meetings with them on this in the future.
Great. Johan, a question for you. Is there a benefit to pumped hydro versus other approaches such as compressed air or gravity storage solutions?
Right. Yeah, so I mean, for energy storage, it's all of the above strategy, I believe. We really have to use what we can. I think there are certain situations where solid-state batteries may be good for, again, shorter duration storage compared to, pump hydro, which is traditionally, a long-term energy storage. So it's really utilizing the right energy storage for the right application.
Rob, we have a question for you. There are some questions about disrupting undersea ecosystems by doing subsea geothermal. How can these risks be minimized?
I'm sorry, what was?
There are questions about disrupting undersea ecosystems. How would you see how these risks can be minimized?
So I think it's a good point. These hydrothermal vents are very vibrant ecosystems. So one is you simply put the heat exchanger above it without disturbing it. The other point is it looks like things like seafloor mining are going ahead anyway. People are using very disruptive dredges from the surface. And so if we can do kind of what I would call surgical mining with autonomous robots, that might minimize the disruption. So it's the seafloor, there's already fishing trawlers already going on there. And so the goal is to try to minimize, by using available energy, what's already going on.
Great. Jim, we actually have 2 questions for you. The first is, you mentioned 80% efficiency for direct carbon fuel cells. What is the basis for that number?
Oh, that's a good question. So obviously we're projecting a little bit, but part of it goes by, what's the theoretical efficiency? And if you look at the PEM fuel cell, it's like 81% theoretical. And today's target's like 60%, and that's basically the best that achieves. Direct carbon fuel cells theoretical efficiency is a little over 100%. And believe it or not, and it's a thermo test for many of you out there, and therefore we just took 20 points off of that. It's like 80%. The single-celled experiments that have done in the past got up to 68% efficiency already, and these were again, university type, laboratory type experiments, pretty quick. So we feel comfortable that 80% is a viable target.
Okay, and then your second question was, how do you envision feeding solid fuel to an electrochemical system?
Oh, that's up for you guys to figure out for me. All right. It's definitely an option, like we showed the different chemistries. You know, you can either leave the solid at the anode. That's the most simple way to explain it, but it's also the most simple engineering maybe solution for it. In the past work, they've added the carbon as a slurry in the electrolyte and introduced that into the fuel cell. And that has worked, like the molten carbonate, for example. Very, very interesting. Again, I think a lot of work needs to be done. Since it's only done on a single cell, yeah, I'd love to get it up to the stack type level to really understand, what is the best way to introduce the carbon and what size. And, that's the real challenge, is how you're going to take that carbon, complete your circuit, meet your ions, and do all that work, and be successful and obviously be economic. So it's a big challenge. It's not easy.
Great. Johan, I have another question for you. Would using pumped hydro in existing mines affect the structural integrity?
Affects what?
The structural integrity.
Structural integrity. I don't think so. I mean, it depends on where the specific mines are. But these mines are typically in a situation where they're in a rock formation where there is actually already a structural integrity. So the only concerns I may have is that, if you have tunnels and these are kept up with columns of either wood or pieces of the mine structure or the coal, it has to be understand what is the structural impact with those, and maybe those need to be strengthened. Yes, but it is sort of depending on the site specific. So but of course, if there are some great ideas coming from the audience, how we can keep that structures in place and strengthen them, please come up with that. Yeah.
Great.
Thank you.
Bill, we have two sort of related questions for you. The first is, what do you define as an alternative fuel? And related to that is, what are the possibilities in using thorium as a fuel?
Oh, two very good questions. So an alternative fuel right now is anything that's basically not the HALEU. And there's several reasons for that. One is we can't manufacture HALEU in quantities enough. That's uranium. This fuel's been enriched to 19% uranium. Ideally, several of the manufacturers have come to us and said, can we come up with a design that would have the enrichment only be 7 to 9%? And that is a lot more easily manufactured and obtainable on that. With regards to thorium, there are some of the manufacturers that we've talked to that are doing microreactors do have the possibility of looking at thorium cycles. But again, like I say, we're not interested in the design of the reactors. We're interested in how you would make them serially. So the question that we would be looking at for thorium is, that's a whole fuel cycle that we don't have existing right now, and how would we make strategic investments into how to provide that thorium fuel cycle?
Great. All right, I have a question for me. What are the cons of using liquid semiconductors? Yeah, I think it's a good question. For all of these examples that I've given, there are pros and cons. With liquid semiconductors, the disordered structure makes sort of like transport more challenging, so then you're getting lower efficiency as a trade-off for higher lifetime. So it's kind of like how we can find the balance of what makes the best system. So yes, again, you guys can answer that question as well. Okay, I think we have time for just one last question. So our last question that came in is for Bill. Can we use microreactors for transportation, like to make electric planes or container ships?
We are part of our request, when we start looking, engaging with industry, we are definitely interested in maritime applications right now. In terms of, what was the other transportation mode?
Planes or container ships?
Airplanes, no. The answer to that is no. The U.S. government back in the 1950s came up with a project called the NB-36. For those of you familiar with this, this is a B-36 bomber, which is the largest bomber ever built. It had 8 propellers and 4 jet engines. And as an experiment, they actually loaded a nuclear reactor into one of these, modifying the cockpit so it was lead-lined, and flew this 100 times. And demonstrated that this was probably the most inefficient use of nuclear power that you could think of.
Makes sense. That makes sense.
Great. All right, well, that is it for us today. Thank you guys very much for coming to the session.